Hey everyone, welcome back. So today we're going to be solving not a question, but we're going to be doing a very interesting concept, right? A concept uh, which which is behind a data structure that is used for a lot of problems, right? So what are we going to be doing today? We're going to be building heap today, right? So many of you would have already used heaps in their problems or in your applications, right? So for example, in Java, what you do is you create priority queue, right? And in that priority queue, you either insert the value, remove the value, perform some operation on it, right? So what we're going to be doing today is we're going to be seeing how that priority queue is built in the backend, right? How the priority queue is being used in the backend, right? How is it working? What is actually happening, right? That is exactly what we're going to be looking into it today. Okay. The reason I'm doing this is because, see, anyone can learn what a priority queue is. Anyone can, do operations on priority queue. It's very simple, right? What does a priority queue do? By default, it's a min heap, and it just removes that, gives you the minimum element, right? If you know the use case for it, you can definitely do it, right? But is that something is that something that a good software developer does? No, right? Because you need to know how it's working, right? To assess the complexity, to assess the scalability, you need to understand how things are working in the backend, right? So that is the reason we need to know. For example, if you're using priority queue, how is it exactly removing an element? What's happening after removing it? What's happening when you're inserting an element? What is heapify? How is the operation log of n to fetch an element or to remove an element? What is exactly happening? So all of this is happening in the backend, and this is what we're going to be seeing. Okay, right. So this is going to be a long session, right? But I promise you, you'll get a complete idea on what heaps are, right? And how heaps are built from scratch, so that the next time you're asked to do it, or the next time you use it, you're aware of what's happening in the backend, right? Okay, perfect. So let's get started. Uh, okay, what is a heap? Before starting anything, what is a heap? Right. Heap is basically heap is basically a tree-like data structure, right? A tree-like data structure. It is not trees. It's not trees. It's a tree-like data structure. Yeah, perfect. A tree-like data structure, right? Which is represented in form of an array. In form of an array. Form of an array. Right? Okay. Now, I mentioned that it's a tree-like data structure. Okay. Um, I don't know how many of you know trees over here, but I'm just gonna. What is a tree? A tree is nothing but a hierarchical data structure which holds nodes, child nodes, parent nodes, all of those things, right? Your heap is also a same thing, right? It is a type of a tree. Let's see. We'll see what type of tree it is, but in general, it's a type of a tree which is represented in the form of an array, right? So in tree, what do you do when you have various nodes, right? In a binary tree, what do we do when you have various nodes over here? How do you access these elements, right? You go to node, and then you go to either node dot left, right, or you go to node dot right, right? So you either go these two directions, right? That is how you do it, and you access the values in form of a. So you access it by reference, right? So how does a tree look? A tree has these things, right? One is a value, right, which stores a value. Here is the left node's reference, right, and here is the right node's reference, right? Reference as an address. So this is what a tree holds, and this is how you access element based on if you want the left node or the right node. So a heap is also a type of tree only, right? Now let's see what type of tree it is, right? A heap, is nothing but a complete binary tree, right? A complete binary tree. What is a complete binary tree? I'm assuming you guys know the definition of complete binary tree. If not, I'll just give you a brief on what it is. A complete binary tree is a binary tree which satisfies a few conditions, right? Conditions where every level except the last level should be filled completely, right? In the last level, everything should be left inclined, right? By that, what I mean is, if you see over here, this is a binary tree, right? This is a binary tree where in level 1, level 2 and level 3, all the nodes are present, right? I mean, like, if you see, this is a complete binary tree. Each parent node has 2 child nodes, and it's a complete binary tree. Okay. Now, there's another tree, right, which can be like this. Right? Is this a complete binary tree? Yes, it is also a complete binary tree. Why? Because there are two things, right? All levels except the last level should be completely filled, right? That is the first one. And what is the second point? The second point is that in the last level, right, all the nodes should be left inclined. What do I mean by left inclined? Let's see. Inclined, right? What do I mean by that is, see, if you see over here, we have, so this is the last level, right? For this, we don't have another node over here. This node is not present, right? So this node is not present, right? But I'm still calling it a binary tree because if you see this node, it is left inclined. It is towards the left, right? Or if I give you a structure like this, right? If I give you a structure like this, is it a binary? Is it a complete binary tree? No, it's not. Why? Because this particular node, it's supposed to be left inclined, right? You're not supposed to have any empty spaces, right? When you write this tree, let's say this is 1 2 3 4 5 6. How do you write a tree, right? You write the parent node, right? Then you write its left child, then right child, then 2's left child is 4 and 5, then 3's left child is empty, and then right child is 6. There should not be any empty node, right? But if this thing was over here, right? This thing was over here, in that case it would be something like this. This is how it would look like, right? This is a complete binary tree. So what is a heap? Heap is a complete binary tree, right? It's a complete binary tree that is represented in form of an array. What do I mean by that? Let's take a look. Okay, now if I actually, let me erase this. Okay, now let's draw a proper tree. Okay, this is a proper tree, right? It'll have 1 2 3 4 5 6 7 8 9 10 11 12. Right? Before I get to that, what are the types of heaps we have? There are two types of heaps. One is a min heap, second is a max heap, right? It is very simple as the definition itself. What is a min heap? It always, on top of a heap, it will always contain the minimum element of the entire heap, right? If you insert numbers in random, like let's say you insert 100 200 90, right? You insert 90 at the end. When you pop out of a heap, right? When you pop the top element of the heap, you get 90, right? Because 90 is the minimum element in the heap, right? We will see how it's built, how it's holding the value, how it's holding the minimum element. But for now, this is what a min heap is. And max heap is exactly the opposite. It contains the maximum element on top, right? Okay. Perfect. Now, like I told you, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? This is this thing. Now, if I have to represent it in form of an array, I'll represent it like this, right? I'll represent it simply like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12, right? Okay. Now, let me index it also: 0, 1, 2. Right. Now, what's happening over here, right? We have represented a form of an array, right? Perfect. Now, you may ask me, Siddharth, if it is a form of a tree, I exactly know how to fetch the childrens of a particular node, right? Now that it's form of an array, how do I know that? How do I know that twos, one's left child is 2 and one's right child is 3? How do I know that? How do I know two's left child is 4 and two's right child is 5? How do I know all that? Right? That's a good question. Right? If you look at it visually, let's take a look. Okay, we have 1 over here, and we need to figure out one's left child and one's right child. Right? One's left child is at this point, right? And one's right child is at this point. Similarly, for 2, if you have to look at the left child and right child, 2's left child is over here and 2's right child is over here. Right? Similarly, for 3, if you have to look at it, 3's left child is over here, 3's right child is over here. Okay. Similarly, let's look at it for 6. 6, where is 6? 6 is over here, right? 6 is over here. 6 left child is over here, right? Perfect. So, do you see a pattern over here? There is a pattern, right? If you see, one's left child is coming up over here, 2's left child is coming up over here. Similarly, it keeps on going, right? So the relationship is that for a given node, or at an index, left child of a node is nothing but 2 into I plus 1, 2 into I plus 1, right? 2 into I plus 1. What is I over here? I is the index of that parent node, right? So just like I discussed, what was I saying? I was saying that for 1, the left child is 2 and the right child is 3, right? If we use this formula, 1 is at index 0, 0 into 2 is 0, plus 1 is 1. We got the left child. Similarly, right child of a node is equal to 2 into I plus 2. Okay, so if you see 1 for 1, 2 into 2 plus 2, right? 2 into I plus 2. What is I over here? I is 0. 2 into 0 plus 2 is 2, which is at 3. So if we got the right child of the node 1 also, right? So this is the relationship for finding out the right and left child. Okay, perfect. Now this is a child relationship, child parent relationship. Okay, now let's look at the this is actually parent child relationship, right? Now let's look at the child parents relationship. How do I know that this child belongs to this parent, right? Child parent relationship. This is very simple. The formula for this is to find a parent at a given node, of a given node. This is a formula: I minus 1 by 2, right? Let's take a look. Let's go to 4, right? Let's go to 8 actually. Yeah, let's go to 8. We need to figure out the parent for 8, right? Let's apply the formula. I minus 1 by 2 is the formula. Let's apply it. I is 7. 7 minus 1 by 2 is 6 by 2, which is 3. Right? Let's look at 3. We got 4. Now let's look at the tree and verify that 4 is the right answer. Yes, 4 is the right answer. Right? Perfect. Now this is a child-parent relationship, right? Okay, perfect. So these two are the main things that you need to remember. How are we accessing the heap in form of an array? Because since it's an array, these two come in very handy, right? Okay, perfect. Now that this is done, let's get to the interesting part, right? What are the main operations on heap that you can do? Okay, let's name it. What is the first main operation that you can do? You can insert an element, right? What is the second operation? You can remove an element, remove the top element, right? What is the third one? Third one is check the size of tail. Check the size of heap, right? This is what we need to do, right? Okay, so we need to figure out a way to do this. Okay, now what we're going to be doing is we're going to be doing this for min heap. Why am I saying we're going to be doing this for min heap? Is that min heap is a basic default structure, right? If you have to use a max heap, you have to either use a comparator or you have to sort it in reverse, right? That is very simple once you understand min heap, right? So now our entire focus would be on min heap, right? So let's build a min heap together. Okay, now okay, see what should a min heap have? Min heap should have some elements into it, right? Only then it can give you the minimum element, right? So what we're going to do is we're going to have an array, right? We're going to have an array, maybe an array list. Let's have an array list, right? Let's keep it dynamic. Okay. Let's have an array list, right? And it'll have certain values, right? Like 1, 2, 9, 3, 4, 12, right? 4 and 12. Let's say this is your array list, right? Now ideally what is the outcome that I want from min heap, right? What is the outcome that I want from min heap? Okay, let's look at it visually. What is a min heap? Min heap is supposed to have the parent of the element. It's supposed to be smaller than its children, right? That is the entire idea, right? Again, let me repeat it again. In a min heap, the parent of a parent of two children nodes, right, should be lesser than those two nodes, right? So that is the idea of min heap. So now let's form it. So we have 1, right? We have 2, right? And then we have 9. Okay, we can't place 9 over here because 9, we can't place 9 over here. Okay, so let's go to the next one. Let's place 3. Okay, if you see, these two child nodes are greater than the parent, right? Now I'm gonna place 4 and 9 over here, and I'm gonna place 12 over here. Okay, this is a form of a min heap, right? Don't get it mistaken, min heap is not sorted. This particular thing is not sorted. This is not sorted, right? This is just a min heap where it follows the criteria that every child node for a parent node should be greater than the parent node's value, right? So that is the idea that heap follows. It doesn't care if it's sorted or not, right? But if you think about it, sorted array is also a form of a min heap, right? If you look at it, if I give you 1, 2, 3, 4, and you simply place it 1, 2, 3, you place it, and then 4 you place it over here. This is also a min heap. This is a sorted array, right? This is a sorted array. This is also a min heap, right? So min heap is like a sorted array is also a min heap, right? Perfect. Now let's get started. Let's code it up, right? And then let's see how things work, right? And based on that, I'll keep on teaching, right? Okay. Now, uh, I'm not using any uh, coding platforms. I'm using this simple online compiler because so that we can code it from scratch. Right? Okay. Now, what we're going to be doing is let me increase this. Okay. Perfect. Right. So I've created a class with heap, right? I've created a class with heap. Now, okay, let's define few things, right? Now, what did I tell you? Heap is represented in form of an array, right? Heap is always represented in form of an array, right? So what we're gonna do is we're gonna okay. So basically, when you have to push an element to your heap, right? Ideally, what would you be doing? You will have some element and you'll push that element into the heap, right? So I'll keep it very simple, right? I'll keep it very simple. I'm just gonna create. I'm gonna have. Okay, I'm just gonna have an array, right? I'll be creating an array list, right? And this will have a integer type, and this will be I'll call it main heap equals to new array list, right? Okay. Now let's define the constructor, right? We'll have the constructor. Uh, this will take in a value, right? Main heap. I'll just call it array, right? Or I can, yeah, or I can just set main heap equals to this dot main heap equals to array, right? Okay. This is supposed to be an array list, right? Okay, perfect. Now I've defined my constructor, right? Now, what did I tell you? I told you that even sorted array is form of a main heap, right? Now let's just say you have 5 elements that you're adding into the array, right? You have to create some sort of main heap, right? Only then we can give in the operations, right? But that what I mean is you can't. So for creating a main heap, right? You have to create a min heap, right? In that min heap, whenever you send in few elements, let's say that let's you send in like 50 elements into that min heap, right? And after that you apply any other operation like you know uh, insert an element or remove an element. All of this will happen in the heap itself, right? So you need to form the heap, right? So we'll be forming the simplest form of a heap, that is a sorted heap, right? So what am I going to do? I'm simply going to sort it. Right? What am I going to do? I'm simply going to sort it. Collections dot sort of my min heap. Okay. Now we have a basic structure of a min heap, right? Let's say you're inputting these elements. Now it will just sort the value and store it in the main heap array list, right? So this will be sorted. This is the basic form of a min heap, right? Now, perfect. Now we need to perform some operations on it, right? So so we have to insert, right? So void insert, and I need to have a value, right? Int value. Okay. Now what happens when we insert a value? Let's take a look. Okay. let's take let's take a simpler okay, let's just actually take this one only, right? Now how will this look? Let me actually bring this down. Now how will actually this look, right? You will have an array list which is sorted, right? And it'll be 1 2 3 4 9 and 12, right? 0 1 2 3 4 5, right? Now this is how your main heap looks, right? This is what we have done until now. Okay, now let's just say that you're inserting another element, right? Let's just say you're inserting, you know what, actually let's start from, let's give it as let's give another value 5. Instead of starting from 1, let's keep it as 5 2, right? So this will change, this will be 3 4, sorry, 2 2 3 4 5 2 3 4 5 9 and 12. Okay, perfect. Now let's just say that you want to insert 1. Sorry, you want to insert 1. Operation is insert 1. That is your operation. That's what you're trying to do, right? Now if you have to do that, let's see what happens, right? Now how does my heap look? The simplest form of heap looks like this: 4 2 3 4 5 9 and 12, right? This is how my heap looks. Now I have to insert 1, right? Where would I insert 1? Let's take a look. Ideally when you're inserting 1, right, you would insert it at the end, right? I'm going to insert it to the end, so I'm going to be inserting it over here. I'll be inserting 1 over here, okay? 1 is what I have to insert, so value is 1, right? I'm going to be inserting 1 over here. Okay, perfect. Okay, now 1 is inserted, right? Good. Now tell me, is this still a heap? Is this still a main heap? No, it's not. Why is it not? Because the most minimum element is 1. The most minimum element is 1, right? But 2 is a 1 at the top, right? 2 is a 1 at the top, right? We need to bring 1 to the top. Only then it'll be a min heap, right? Why? Because whenever you're popping an element out of a min heap, you'll always get the minimum element in the array or minimum element in the min heap, right? If you pop it out now, you'll get 2, which is wrong because 1 is the minimum element in the min heap, right? So this is what we need to do, right? So what are we going to do? Very simple. It's very, very simple, right? We're simply going to check the parent. Check the parent of 1. What is the parent of 1? Parent of 1 is nothing but 4. Parent of 1 is 4, right? Perfect. Parent of 1 is 4. Now we're going to check, okay, I have my parent, right? My parent value is, if my parent's value is greater than my value, right? So let me swap it. Okay, so what am I going to do? I'm simply going to swap it. Okay, why can I confidently swap it? You might ask, Siddharth, what about the left element? Are you not even considering it? What if that changes? What happens to it, right? We don't have to worry about it. Why? Because if you're 1, if this element is lesser than this element, right? This element is less. I know for a fact this element would be lesser than this element. Also, this element would be lesser than this element. I'll know that for sure. Why? Why am I saying that? Because how are you storing it in a min heap? You're storing an element, that you're storing some element, and this element is like you're storing, let's say A. This element is greater than A, and also this element is supposed to be greater than A. If this element is less than A, when I shift it over here, this element will get swapped. Right? This element will get swapped. Since this is lesser than A, this definitely be lesser than this also. If this is lesser than this, if this one is lesser than this one, then this one will be definitely lesser than this one. right? It'll be definitely lesser than that one, right? So perfect, we know that. Now we can swap it. What am I simply going to do? I'm just going to swap it. Okay, I will perform a swap where this will become 1 4 1, and this will become 4, right? Perfect. Okay, now again I will check the parent of this. Okay, it is small, we're going to do the same thing. So now how will it look? This will get 1 and this will get 2. Perfect. Now how does my min look? 3 2 5 9 12 4. This is how my min heap is. Is this following a structure of a min heap? Yes, it is following the structure of a min heap. I don't care how the elements are stored. I just want the minimum element on top, and it should follow the criteria where child nodes are greater than the parent nodes. That is all I want. I don't care if it's sorted. I don't care how it's stored. Right? This follows the structure. Right? Now you might have had a question: if you're building a min heap, why are you sorting it? This is exactly why I'm sorting it. If I had not sorted it, how would I know? How would I know that? How can I say that how can I say confidently that if my child is less than my parent, I can swap? I cannot confidently say that, right? If I have not created a simple min heap in the start itself, I cannot confidently say it. Now that I've created it, I can confidently say and I can confidently make swaps so that the minimum element comes to the top, right? Perfect. This is exactly what we're going to be doing. So until what condition are we going to be running? One is until we're going to be running it until I is greater than 0. Right, greater than or equal to 0 also. Yeah, greater than or equal to 0, and array of I, right, that is the child node, is less than array of I minus 1 by 2. These two are my conditions that my while loop is going to be running under, right? So what are we going to do? Simple. We are going to insert it in the end. What is the first operation? The first operation is to insert it in the end. This is the first operation, and this is the second operation. Right? Let's code it up. Okay. So what are we going to be doing? Since it's an array list, I can just add, right? I can say min heap. Why is this not giving any suggestions? Okay. I'm not sure. Okay. Min heap dot add. I can just add the value, right? Add the value. Okay. Now, index equals to min heap dot size minus 1. Right? That's my index. Perfect. Now that I've added it, I have to, what do I have to do? I'll have to do this swapping so that it is a min heap at the end, right? So that's exactly what I'm going to be doing. While I is greater than or equal to 0. No, I should be greater than 0, right? Because you're doing I minus 1. If it's 0, why will you be doing 0 minus 1, right? Perfect. And min heap of I, min heap of I, okay, sorry, dot get of I is less than min heap dot get of I minus 1 I minus, oops, I minus 1 by 2. Perfect. right? Okay, what are we going to be doing if this condition is correct? We're going to be swapping, as in if this condition goes through, we're just going to be swapping. We'll call swap of I, comma, I minus 1 by 2. I minus 1 by 2. We'll write the swap function later. It's a very simple swap function. We'll write it later. Right? But ideally, this is what I'm doing. Perfect. Written. Done. So we are done with our first step. Insert an element. It's as simple as that. Right. We're done with the first element. Now it is a void function. Why? Because it's not going to return anything. It's just going to insert a value. Now remove. Remove is where it gets very interesting. Let's discuss about it. Before remove, let's just discuss the size of heap. It's very simple. This will return an int, right? So public int size. I'll just this will just return main heap dot size. Right? Perfect. Now let's come to the interesting part. That is nothing but my removal operation. Okay. Let's look at the same example Okay. Now this is what my heap is, right? And I need to remove an element. What element will you be removing? Will remove the top element, right? That is this particular element you'll remove, right? You need to remove this particular element, right? Okay. Now, what are we going to be doing? It's very simple. When we are removing this element, okay, what we're going to be doing is we will swap this element with 4. We'll swap this element with 4. I'll tell you why. We'll swap this element with 4, right? So what will happen? 4 will come here, 1 will come here before removing, right? So how will it look now? It will look something like this now. When you swap, after you swap it, it looks something like this, right? That is 4 1. After I swap it with 4, why am I swapping it with 4? It's the last limit. I'm swapping it because of that. Why exactly are we swapping it? Why can't we just remove it? We'll talk about it. But if you just think about it, it's very simple. Why will you remove the top of your root of your tree, right? You don't do that because your entire tree will fall, right? So what do you do? You send it to the bottom. You remove it from the bottom, so the top always has some value, right? That's exactly what we're doing. After we remove this is when we will detach this particular. Okay. Now we have removed one, right? We will return it. Okay. Now we have returned it. Now you might ask me, Siddharth, if you look at this now, this is not a min heap, right? This is not a min heap. Why? Because our minimum element is 2, but the element on top is 4, right? This is not a min heap, right? This is where we'll be applying an operation called as heapify, right? Let's see what that heapify is, right? So what are we doing? You have this 4, you have this 2, you have this 12, right? In the insert, what do? We check from a child to parent. This exactly opposite we'll be doing. That is what heapify is. We'll be going from a parent to the child. That is a left child or a right child. you'll be going from a parent to a left child or a right child, right? Now you're at 4, right? By that what I mean is from 4, right, from I equals to 0, right, you'll be going until again two things, right? Two, what is that two things? The first thing, the first criteria is the parent, that is array of I, should be less than, array of I should be less than array of I should be less than array of 2I plus 1 and array of 2I plus 2. So only when this case, right, I is less than array dot length, okay, wait, actually I is okay, let's come to that condition. But until this condition, you will be doing this operation, doing this heapify. Okay, now this is the condition that I have, right? Perfect. Now let's do it. What am I going to do for 4? I'm going to check the left child and right child of 4. What is the left child of 4? Right, now if you see, if you look at the array, this is how the array looks, right? So 4, 3, 2, 5, 9 and 12 is over here, right? And index is at 0, 1, 2, 3, 4, 5. Okay, now 4 is at index 0. I need the left child and I need the right child, right? So left child will be 2 into I plus 1, which will be nothing but 2 into 0 plus 1, right? Right child will be index, this is the index, right? 2 into I plus 2, which is nothing but 2 into 0 plus 2, right? I'm going to be comparing it. So 4 will get compared with, that is 3 or 2. Okay. Now when I compare it, right, the minimum value from here is nothing but 2. When I compare these two, the minimum value is 2, right? The minimum value is 2. Now what do I have to do? I have to swap it with 2. Simple as that. Now what I'll do is I'll simply swap it. That is, I'll set 2 over here, I'll set 4 over here. Done. That's exactly what I'm doing over here. So here we'll swap it. We will make this as 2. We will set this as 4. Done. Now let's look at the heap. 2 is on top, 3 is over here, 4 is over here, 5 is over here, 9 is over here. Perfect. 12 is over here. Perfect. Now does it form a heap? Yes, it forms a heap. Where 2, you have 3, you have 4, you have 5, you have 7, you have 12. Right. Perfect. Now till where will you go until? Last time we had a condition, right? Now just for this time, where will you go until? Right? We can do one thing. We can take I until where can we take I until? Okay, let's actually take a look when we're coding it. Okay, let's just start coding it. Okay, now what did I tell you? Public int remove, right? Public int remove, right? Here, what will I do? I will swap. What am I swapping? Swap 0 with min heap dot size minus 1. This is what I'm swapping. After swapping it, int value should be my heap dot remove my heap dot size minus 1. Okay, this is the value. Okay, I will return the value. Before returning the value, I'll call something as heapify. Then I'll return value. Okay, now what is heapify? We're gonna give it as a private function because others do not need to know do not need to use it, or do not need to know what's happening inside, right? So private void heapify. This is why will be doing our logic, right? So at heapify, what is it? Int I is 0, right? Int I is 0. Now, where will we go under? Let's take a look into that later, right? So what I'm going to do, I'm simply going to define my while loop. I'm going to leave it empty, right? I'm simply going to define my while loop. Now, okay. Now, int left child will be main heap of 2 into I plus 1, right? 2 into I plus 1. Oh, sorry. Main heap dot get off 2 into I plus 1, right? This is my right child. Int right child. Now tell me, right child, should I give it as min heap dot get 2 into I plus 2? Should I give it like this? No. Why? Because a parent can have a child node for sure, because we are doing it as left inclined. Because we're using complete binary tree, we know for a fact you will have a child node unless and until it is a leaf node, right? But our node, our parent node, might not have a child node, right? It makes sense, right? If you take a look into this example, right? If you take a look into this, for this particular node, right? For this node, I have a left node. I'll have it for sure, but I don't have a right node. When you try to fetch this value, it's gonna throw you out of bound exception. So you need to check that first, right? You need to check that. There are various ways to do it. It's just the way that I'm doing it. So what I can do here is I'll remove this. Okay. What I'm gonna be doing is I'll set it as integer dot max value. Okay. Why max value? Why did I set it as max value? You'll get to know, right? You'll get to know. Now, what am I going to be doing? I'm simply going to be before I check what is the minimum value, I need to fetch the right value, right? If I think I can just paste it over here. Okay. If 2 into I, if 2 cross I plus 2 is lesser than min heap dot size, I know for a fact it is lesser. 2 into I plus 2, right? 2 into I plus 2 is lesser. Only then my right child will have min heap dot get of 2 into I plus 2, right? Perfect. Of 2 into I plus 2. Right? Now, what am I going to be doing? I need to take the minimum value. Int min value will be max dot min of what are now values am I comparing? I'm comparing the current node value, the parent value, and 2 of its child value. So the parent value will be min heap dot get of I, comma, left, comma, math dot minimum of left child, comma, right child. Right? Left child, comma, right child. If min value equal to my parent value, that is min heap dot get of I, right? Which means that I don't have to do anything. I can just break. If my min value, why am I breaking? I hope you understood that. The reason I'm breaking is I found out my min value, right? See, what is a heap? It is storing a minimum value and all its children are greater than that, right? If I'm comparing my parent value and two of its child value, right? If my minimum value itself the parent value, then that is following the heaps property, then I can break. That's why I'm breaking, right? If my min value equals to left child, then what am I going to do? I'm going to swap it with left child, right? I'm going to be calling swap of I, comma 2 into I plus 1, right? If my min value is equal to right child, then what am I going to be doing? I'm going to be swapping I, comma 2 into I plus 2, right? Down, right? As simple as that, right? As simple as that. Now, are we missing something over here? Yes, that is what comes under the while loop. Also, one more thing, right? I just forgot about it. We need to set the I value, isn't it? We need to set the I value. Why? See, right, we need to set the I value. Why? Why do we need to set the I value? 2, 3, let's just say there's something over here, and then there's 4, and then there is 1, and then there is 12, right? Let me actually switch these two. This will be 4, this will be 2, right? Now, when I check 4's child, right, 2 is lesser than 4, so I'm going to make a swap. So what's going to happen? 4 is going to come here, 2 is going to come here. 2 is going to come here, 4 is going to come here. Right? I made the swap. Right. Now, my eye is currently pointing at this particular point. Right? My eye was pointing over here. Now my eye need to point over here, isn't it? Because I'm going to be checking these two values. Right, I'm going to be checking these two values. Okay, I mean, this won't be over here because your heap would not have that. Let's just say this is 13, right? So my eye needs to come over here, isn't it? If this was 4 and this was 2 instead, right? I will swap these two. Instead of these two, I'll swap these two, right? When I swap these two, my eye needs to come over here, isn't it? To check the other values. My eye needs to come over there, right? I need to make a swap, right? So I'm going to be making a swap. So I mean, I made a swap. I need to set the I value, right? If it's left child, it's simple. I will be equal to 2 into I plus 1, right? If it's equal to the right child, my I will be equal to 2 into I plus 2, right? As simple as that. Let me add brackets over here. So yeah. Now, what will come under while condition? See, if you think about it, what can we add into the while condition? Either you can add I is less than 2 into I is less than sorry 2 into I plus 1. Yeah, 2 into I plus 1 is less than heap min heap dot size. Why am I doing this? Wait, or you can also add and no, you cannot add that. You can add, no, what I thought is I'll add it for right as well, but like I said, a node might not have a right node, right? It might not have a right node. Okay, this is a safe condition. Why? Because what are we doing? I'm assuming for sure that, I know for a fact left node is gonna be there, right? Left node is gonna be there for a parent node, right? If the left node is not there, that is if it is the leaf node, right? That is for this. If it's checking this, which is not present, in that case it will break. Because every other node is supposed to have a child node. If it's there in the heap, it is supposed to have a left child node, right? It won't be present only if it's a leaf node, right? Only then it will be present. So this condition will do. Perfect. Now we're done. We just need to add okay, we just need to add this thing, that is swap, right? It is okay. Now I've added ep5. This is my okay. Now this will also be private, right? Void swap, right? I'll just call it int left, int left, right? How do I swap? I will just take int temp equals to main heap dot get of left, right? Main heap dot set at left is main heap dot get of right, right? Main heap dot set of right, comma 10. I'm setting the value as 10. Perfect. Done. Okay. I think we've done good. Okay, here we didn't set the I value, right? I'm gonna be swapping it. We need to set the I value. Right. It's the same thing, right? It's the same thing. Right. If from a for heap5, what do we do? Where do we set the I value? When the I was at parent, if it's moving to left, we're setting it to the left child. If moving to right, we're setting it to the right child. But in terms of this, since it's going to the parent, we will set I to the parent, right? I equals to I'll just use this. Perfect, right? Okay. Now let's try it out. Okay, let's create a class, right? My heap equals to new. Actually, I'll have to give an array list, right? Array list of teacher equals to new array list, right? Let's just add few elements to this. I'll call it array, or I'll call it list, right? List dot add of I want to add 1, right? Similarly, I want to add okay, I'll just add these 4 values, right? I want to add a 2, I want to add a 1, I want to add a 3, I want to add a 4, I want to add a 9. Well, let me add one more value. I want to add a 12. Okay, so So when I run this test case, so I've just created a list, right, and I've added these values, and then I've created an object of the heap class, and then I'm inserting 0, and then I've given remove, right. So now it should remove 0, so the output should be 0. Let me run it. Perfect, output is 0. So let me insert -1, right, and then let me give this thing remove. The output is -1. Perfect, perfect. Now after I insert, I will just check the size, right. The So just to make sure that's inserted, right, how many inserts are 1 2 3 4 5? It should print 6, right, because you've added one element over here. Perfect, right. Yes. So we know for a fact our heap is working, right. In Maxi, all you do is you just reverse it, right. It's very simple. You just reverse it. Okay, perfect. Thank you so much for watching. I hope you understood. Though this was a long video, I really hope you understood what we were doing. Right? I would suggest you to do it on your own so that you get a very good idea. Thank you so much. Bye bye.